All right, so first off, thank you. I understand that it is a commitment of time that is oftentimes a very limited resource for all of us, especially those in the water industry, and I'm assuming we all are. And so we appreciate you taking the time to spend it with us and the Transcend team today. We don't take that lightly, and it is a commitment. So again, thank you for joining. By way of introduction, my name is Adam Tank. I'm the Chief Customer Officer at Transcend. Effectively, what that means is I work with our customers to ensure that they're getting value from our tool. So that would be our EPC clients like Black & Veatch. It'd be our utilities like United Utilities and others in the UK and of course in the US. And then our equipment suppliers, folks like Suez, DuPont, and others who provide equipment to treat water and wastewater. Today, what we're going to be showing you is how our clients utilize the Transcend tool, the Transcend Design Generator, to generate preliminary designs of treatment processes, and specifically we'll be talking about biological phosphorus removal. So without further ado, I want to introduce you to Nikolett, or Letty. She's a lead process engineer on our team at Transcend, and she will be presenting to you today not only why the software is valuable and how people use it, but how it works and a little bit around the technical side. Letty.
Nice to meet you, everybody. I think let's just jump in. So I will share my screen and start the presentation with what I have prepared for today. Okay, here it is. Okay, so what I will show you today is a short overview about the structure of the tool, then saying how it works, how the different parts of it are connected, and what exactly the tool does, what are the inputs, what are the outputs, and what's happening in the background. And this, what happening in the background question will be mostly about the BioP concept. This is a quite new feature which we have just introduced to the tool. So I will show you how the system will design a BioP activated sludge facility and what are the background calculations, what concepts are taken into account when we do the design at the background. After that, I will show you the user interface for those who are not familiar with it, including the BioP functionality, the BioP selection points, and I will show you all of the output documents which are generated by the tool. And if we have time, and I hope we will have, I have prepared a really mini feasibility study for you to show that how the tool can be utilized to compare different options and why it can be done very fast using the design generator tool. So yeah, and as Adam mentioned, put any questions into the chat box. So what's the structure of the tool? On the left side, you see the data validation and the data input part. This means that we have a user interface where you have to enter all the data related to your facility. This means influent flow, influent concentration, and of course, effluent concentration requirements, and some additional features which you would like to have. For example, you can select whether you would like to have a primary clarifier or not. So technically, you can just configure the facility, what you would like to get from the design generator to be designed. When all of this is done, we start the process part at the background. So we select the different units which you were asking for, sizing each of them separately first, the clarifiers, the biological reactors, and so on. And when all of these pre-calculations are done, we are verifying everything with a steady state simulation. We are utilizing Simba at the background. So we put together the full layout, running the simulation, and checking whether with those conditions, those recirculation ratios, which we have pre-calculated, the facility will meet the limits or not. If not, then we are adjusting something within the facility, like reactor volumes, DO set points, recirculations. So anything what you would do manually, this is done by the tool here. And when the steady state simulation has reached the point when it's saying that the limits are met, so this facility is going to work, Then we are also running a 1-year-long dynamic simulation where we are taking into account the yearly variations in the temperature and of course the daily fluctuations of the influent wastewater. So when all of the process calculations are done, the system is jumping to the mechanical part, meaning that we are selecting different equipments for all of the units, like the centrifuge, thickeners, and so on. We have an equipment database at the background. So taking into account the, let's say, the required flows, we are selecting the proper equipment for that, also for the blower and so on. This means that as the equipments are there, we can put together the electricity-related calculations. So we are creating a load list as well, which can be used for the OPEX calculations. As a next step, the architectural part is coming in. When in Revit, we are creating a 3D BIM model of the full facility which the system is proposing. So building all of the concrete structures and so on. And the last part is the document generation, which means that from this Revit file, we are creating PDF exports, renderings. We are creating process scheme or a process block diagram showing what are the different units in the facility. And as I mentioned, regarding the mechanical part, we are creating an equipment list and a load list from all of these calculations. And actually, these are the output parts of the tool. And this is shortly what's happening at the background. Of course, this is a general, very high level overview of it, but I hope this gives you a little bit chance to understand what's going on. Okay, as I mentioned, I want to focus on right now more on the biological phosphorus removal. So first, this is a mainstream biological phosphorus removal, which we are offering right now. As I think all of you know, that typical conventional design says that anaerobic retention time of 1-2 hours is required for a proper BioP performance. However, we have checked quite recent publications, which are saying that, as the common knowledge is that it is quite hard to operate BioP facilities, they are many times not working properly and so on. And the reason of this is that because of this general 1-2 hours retention time is, in many cases, is not enough. The design shouldn't be based on the retention time, but it should be based on the anaerobic mass fraction available for the facility. So this is what we have incorporated into our calculation. So as you can see here, that this is considered in initial calculation. So we are taking into account SRT calculations, typically from Metcalfe and other textbooks, and those general sizing logics which are available publicly. And this is, and upon this, we have added this biological phosphorus removal part. So we are calculating the anaerobic part, anaerobic reactor size based on the required anaerobic mass fraction. And after that, as we are coming to the modeling part, our previous models were not using the phosphorus accumulating and the glycogen accumulating bacteria within the model. So also the SIMBA model is updated to have these available, which means that the simulation as well can check and show you the biological phosphorus removal performance of the facility. And this chart, which I'm showing you right now, is coming from that specific publication I have mentioned previously. So the author said that about at least 0.2% of anaerobic mass fraction, 20% of anaerobic mass fraction is required to have proper BioP performance. However, they are saying that the phosphorus to be removed and the influent COD, the ratio of these two parameters are the main drivers which tell us that what should be the proper anaerobic mass fraction. So if you can see that if this ratio is quite small, then we can go with lower mass fractions, and as this ratio is going up, we will need higher mass fractions in the facility.
Hey, Letty,
yeah?
We have one question in the chat. So Hung asks, how can we run dynamic simulation at a pre-design phase when dynamic data is not always available?
Good question. Actually, we are generating this. So if we are considering the temperature, that's typically always available, that what are the minimum and the maximum temperatures. And the other part regarding the flow is if you have already the information about the average flow and, for example, peak daily flows, so how the daily flow varies during one day, that could be entered. And also, the design generator has the function that if you know only the design average flow for your facility, then we are calculating the typical population equivalent from that, and also from literature, from Metcalfe-Kennedy and other textbooks, we are calculating a peak factor, which is typically proper for that specific population equivalent. And we are using that value to create the diurnal flow variations for the flow. So this is considered for the dynamic simulation. So we take into account the daily flow fluctuations and the temperature variations throughout the year. Why it is also important to have this? Because that yearly simulation is used to get the maximum airflow rates for the blowers, for example. So this means that all of these factors are taken into account. Okay, so back to this question about the anaerobic mass fractions. This was the original chart shown in that literature, that paper. We have just transferred it to, as user is entering what is the input, influent and effluent phosphorus, then of course the delta TP could be calculated. The influent COD is also known. So we are getting the X values of the chart, and we have just created this equation down here to get the required anaerobic mass fraction. So this is the calculation background. This will lead us to the anaerobic volume of the reactor system. What configurations are supported? These can be selected from the user interface. So the two, of course, there are others, but we have selected the two main configurations which are typically used. One is the Barden-4, or commonly known A2O, and the other one is the UCT configuration. So these are the available options. As you know, the only difference is that within the A2O, the RAS is directed back to the anaerobic reactor, but for the UCT, the RAS is directed back to the anoxic stages. So we are not bringing back any nitrate to the anaerobic part. But in this case, an additional MLSS recycle should be added to have proper MLSS at the anaerobic reactor at the very beginning. Also, both configurations can come with a post-anoxic zone with carbon addition after the aerobic phases. This is just required in case when the TN limit is quite low, and this original configuration cannot meet the total nitrogen limits. This happens quite often if we are considering a BIOP process, because many of the quite high part of the readily biodegradable substrates are consumed in the anaerobic part. So less is available for the anoxic part. So this is how we solve it with the post-anoxic extra reactor added to the system. So I think this is what I have prepared to say about what's at the background. And if you don't have any questions regarding this, I would jump to the user interface now and show you how it looks like exactly.
No questions in the chat, Letty.
Okay.
So feel free.
Okay, so this is our user interface. And I'm just starting a new project now. And filling in the data here. So first, we are asking for some project-related information. And you can select metric or imperial units. You can select the location of the facility. And it is possible to, if you have already selected site, then you can go with this one and you will see a map and you can mark on the map that you where will be your facility. And also it is possible that if you have already existing assets, which you would like to repurpose, then you can go also this way and mark them on that map. And then the design will take that into account. Now, in order to make it a little bit faster, I'm just going with the no site selected version. So we are skipping the map because I want to focus on the BioP functionality only. This bottom input field is just helps you to have some rough typical effluent limits available in the selected country. So we have a background database about each country in the world or each region in the world. And we have collected the typical requirements. And later on, you can select these typical requirements if you don't, for example, you don't know all of the requirements, but you have. So now we have just arrived to the point when we are asking for the influent design temperatures. As you can see that here, based on the region, we are offering typical values, but you don't have to say that's okay. You can always overwrite that value. Let's go, I don't know, some kind of design flow for the biological system. And regarding the previous question, if we go here to the advanced part, here you can enter peak dry weather flow, peak daily flow, and so on. If you have this information, and if you have, then these all will be taken into account in the dynamic simulation. And as I mentioned, if you just leave it empty, don't fill it, that means that the system will calculate it for you.
Hey, Letty, we have a question on warm climate temperatures between 30 to 35 C. So when the GAO bacteria may overcompete the PAO, can we still have effective BioP? And how to overcome
Actually, the fact is that this system is limited to 35 degrees. So you are not allowed to enter higher temperatures for that. So yeah, this is for these reasons that above that temperature, there might be problems and the system behaves a little bit differently. And these are not factored into the tool. So that's why we are limiting it. If this answer was proper, I hope so. So now we have arrived to the influent concentrations. Again, based on the region, we have some typical numbers here, which we can just accept, but also we can change it. So let's say I'm going with a little bit less TKN and maybe I have less phosphorus as well. You can enter either TKN or ammonia or both of them. So if you're just entering one, then we are assuming the other, but you can you have the possibility to enter each of them. The same as for the phosphorus. And this is something I wanted to show you. And as I mentioned that this data, what you are entering here is validated by the tool. So what we are not allowing is to enter non-reasonable data sets. So for example, this is not maybe a huge problem, but if you just switch the COD, BOD and things like that, the tool itself will check whether the data set, what you have entered is proper. And if not, then you are getting some error messages like this, and you cannot even move on to enter your additional information regarding the facility. So I was changing it a little bit back, and now I can move on. So this is how we protect the system from data sets which are improper and would cause problems, especially, for example, within the model. Now we have just arrived to the effluent concentrations. Again, we can accept them, but if we are not having these values, then we can change them. So I'm, let's say, going with the TN10 facility, and maybe for the phosphorus, I have 1.2, just as an example. Okay. As we have now all of the information regarding the influent flow, now we have arrived to the technology-specific selection options. We are allowing to select the different grid chambers, aerated or non-aerated, or you can still say that let the tool decide. Flow equalization, the same. Primary clarifiers, this is something already I have mentioned. If you're asking for a primary clarifier, we are offering you that you can give the design hydraulic loading rates for the average and for the peak conditions. Of course, we have defaults for all of these, but you have the possibility to overwrite our defaults with your target numbers. Now we have arrived to the technology selection. Now I will just move on with the CAS. But these are the other systems which are supported by the design generator. So it is possible to select all of them, but it's possible to select only one or two or anytime you want. If you select all of them, that means that 5 different designs will start when you push the start design at the very end of the user interface, and you will receive all design documents for all 5 technologies, so you can easily compare them. So another input field is the number of biological trains, chemicals for phosphorus removal. Of course, if we are going with the BioP, then there's no chemical used, only if it is calculated that the BioP will not sufficient and cannot take all of the phosphorus away. So typically below 1 milligram per liters, we are always adding chemicals as well. So that 1 milligram per liter in terms of effluent phosphorus limit is the line which we have defined that can be achieved by pure BioP, but below that we always go with extra chemical to make sure that the facility can work properly. And for example, other questions, let's say we can select also disinfection. We have UV and other chlorine-based systems available. So these were the general technology-specific selections, and now we have arrived the activated sludge specific selection. So if you select all of the technologies, then you will see here a few more pages at the top. So next to the CAS, you will see the SBR, the MBBR, and so on. And you will have a different page for all of them to define the different technology specific parameters. The first one is the minimum aerobic SRT. As I mentioned, there is a calculation in the background that is based on the Metcalfe-Kennedy calculation, which is taking into account the effluent ammonia concentration and the temperature, of course. And here is the button for the biological phosphorus removal selection. So let's go with the yes now. And you can select here the preferred configuration, the UCT or the BARD info. As we have the clarifiers, the secondary clarifiers at the end, we are providing also the hydraulic loading rate input fields here, and also for the solids loading rate. So We are taking into account all of them in the calculations, and the biggest one will be the driver, so to size the secondary clarifiers. Regarding the tertiary filtration, we have disk filters and pie-closed medial filters available now, so you can select from these. And that's it for the CAS. So as I'm pushing the next button, we have just coming to a summary page because we didn't have any other technologies selected. So that's it. And I'm just pushing the run design, and the system will start to do the calculations. Typically, it takes about 8 hours to get the design documents, depending on the technology itself. A CAS system is maybe a little bit faster, not even 8, but a little bit less hours. But if you go with an MBBR or an MBBR IFAS, which is a biofilm system, in that case, it can take a little bit longer because the biofilm system is also modeled. So that is sometimes a little bit slower. But regarding the CAS, we are expecting something within 8 hours to have available.
One thing I'll mention, Letty, and to those that are on the webinar, what Letty just did in the span of about 10 minutes typically takes our clients, either the equipment suppliers or the engineering firms, weeks to complete a complete conceptual design package for an activated sludge system with BioP. So in just 10 minutes for a greenfield facility, obviously we have a brownfield capability as well, and you're welcome to try out the tool for yourself. The link is in the chat. It's a very short amount of time and effort to get a complete design package. And what we mean by complete preliminary design package is exactly what Letty is going to show you right now.
Yeah. So now I'm just planning to walk you through the output documents. So yes, as Adam said, this was the only time I had to spend on my process design. And within 8 hours, I'm having all of these documents here at the bottom. And I'm just walking through them to show you what we are producing. So the first one is the process scheme, is the kind of block diagram, screens, grid removal, primary clarifiers, and I'm just zooming in to see what's inside. So we have the anaerobic reactors, volumes. So it's just a common process scheme with all of the recirculations and so on. So for example, here, this is a microfiltration unit. So everything is listed here. And besides this, we put together a technical description, which is, I would say, contains a little bit more information compared to the process scheme. So we are describing everything quite detailed, that what should be there within the facility. So now I just zoomed into the biological reactor part for this. So we are providing the final SRT, the final MLSS concentration, excess solids, methanol dosing requirements if it is required. So everything what should be there at the facility is listed here. Number of clarifiers, side water depth, and so on. And as I mentioned, that it's showing this. Okay. So we are selecting the equipments. We are providing a full equipment list. So all of the units which should be present at the facility are listed here, like separate blowers for the sludge storage tank, centrifuge, whatever, polymer dosing, pumps, and so on. And as all of them are selected, we are calculating the load list. So all of those equipments are listed here with the proper motor power ratings and demand factors. And in the end, we have the daily average consumed power totalized here down. And this information, together the other data gathered from the process design, a final OpEx table is put together. So we are listing here the methanol requirement, the polymer, the sludge, and so on. So if you have this, that is just summarizing you all of the OpEx related information.
Hey, Letty, we have a question in the chat.
Yeah.
So Mikhail asks, what are the guarantees for the correct operation of the proposed system?
Actually, this is a preliminary design. So taking into account that we do the pre-calculation, preliminary calculations and the verification with the model, we are quite sure that at this level, this guarantees that this is going to be work. Of course, later on in the later phases of the project, when you have detailed information regarding the influent concentrations, fractionations, within the tool, we provide some fractionation, of course, because we have to be able to run the simulations. But that fractionation is just considering some typical fractions, which are commonly there for most of the facilities. But if it turns out that you have a different fractionation, that of course can influence the design, but that comes in later phases. So I think that, as we are always saying, that this is a preliminary design, the level of detail and the accuracy is on the preliminary design level. So of course we cannot factor in very specific fractionations, for example, but that comes in a later phase. And you are also able to download the editable files, including the simulation. So for example, if you have later on in your project detailed information about your influent fractionation or something changed within your flow conditions, you can easily just run the simulation by yourself to make sure that the system is still working properly. Of course, we are taking in, yeah?
Go ahead and finish. We do have another question.
Okay, so what I just wanted to add is just, yeah, we have a safety factor for the SRT, for example. So those are factored in. And one thing, as you have seen that, for example, this SRT is allowed to be a user input. As we do the modeling, we try to meet that specific SRT. But for example, if the model is saying that with that specific SRT, this system will not work, the effluent limits are not met, then we are just dropping the user input SRT and increase the SRT until the system is able to meet the limits. So these are the things which we are trying to make sure that the system will function properly. Yeah, Adam,
Letty, AJ, yeah. Yep, that's great. So AJ, thanks for joining. For the mechanical equipment that is generated, is this actual available models for manufacturers or just a calculated number?
It depends on the equipment. So some of the equipments are calculated, and we are just giving the motor power rating. For example, for the blowers, we calculate what the size, but for I would say half of the equipments are also actually selected from a vendor database. I mean, we have the specifications from the vendors, and those equipments are included and then selected for the facility. Adam, do we have any other questions, or I can just move on?
Nope, you're good.
Okay. So this was the end of the equipment part. And now I'd like to just move on to the civil part. So as I mentioned, that we are creating a Revit model, a 3D BIM model. And that BIM model is used to generate, for example, this site plan, what you can see here, with the different clarifiers and so on. And also, this is the rendering created from that specific facility. So it looks like this. I'm just zooming in. But also not these PDFs, but here again, the Revit file is available to be downloaded. So if you don't like the arrangement or anything regarding this, you have directly the Revit file, and you don't have to build up it from zero, but you can take it and just do the arrangement how you would like to prefer to have. And from this civil drawings and from the Revit, we are calculating civil BioQ as well. So different items here, site preparation works, and so on, different concrete types, the amount of them, and so on. So all of these documents are available to download after 8 hours. So it means that you have just spent about 15 minutes entering the data, and you are getting this full document package within 8 hours. And you can move on with your preliminary design for later on for design detailed phases as well by taking the model itself. So I think that's it, what I just wanted to go through and show all of you. Do we have any other questions?
We typically get a lot of skepticism. So if your question is, I don't believe you, how does this really work? That's totally acceptable. And it's one that we hear quite a bit. When we tell people we can generate a complete preliminary design package in less than 8 hours, something that typically takes hundreds, if not thousands of hours, it can be challenging to sort of wrap your mind around that. AJ believes me. Thank you, AJ. Vote of confidence. Okay, we will keep the webinar open for another 5 minutes or so. Anyone is welcome to go. We appreciate you joining, and we will be sending you the recording and a link to log in, and your first design is on us. So we hope that you try out the tool, and we hope it's helpful for you as you generate conceptual designs of wastewater treatment works.
Hi, Adam. Can you hear me?
Hey, AJ.
Hi, I've got another quick question for you. You showed us a couple of configurations of BioP. There's been a trend for sort of other configurations like side stream anaerobic zones, for example. Have you got any plans of incorporating those into the design, or is it already there? I'm not seeing it.
Actually, it's not only there. Now it is only the mainstream version of BioP. But yes, we are aware of it, and this is in the plan because it's not only you asking this, and we know that it's quite an interesting topic right now. And at many cases, side stream versions of BioP are more efficient. So, but yes, the first step was to add for the mainstream, and the side stream is just coming later on.
Brilliant, thank you.
All right, so 2 more questions. Let's see, I don't know if you can see these. We often prepare designs to implement IFAS to upgrade plants for BioP. Can you include IFAS into your calculations, most specifically for utilizing existing assets? That's from Lewis.
That's a very good question, yeah. Actually, IFAS is already there, as you have seen at the technology selection. I was just not doing that. And I can tell you that right now, the BioP selection option is available for the SBR and for the CAS. So for the IFAS, it is coming in the next week. Actually, it is in testing at the background, so it's testing phase. So you can expect it the next weeks to have it live on production. And yes, it can do for existing assets. So as Adam mentioned, that if you are logging in and trialing the tool, you will see that how it is going with the existing assets. If you select the version when you have existing assets, you will see a map, and you can mark all of your existing assets. You can give us the volume of your existing tanks, and then we will try to make the system fit in to that tank volume. But if it's not, then we are just providing what amount of new reactors should be built if the existing part is not sufficient. So that's the brownfield part of the tool.
Letty McHale asks, are there any documents with limitations and constraints in the model? For example, the length of pipelines or the head of pumps?
So actually, the pumping system, I mean, not the pumping, sorry, the piping system is not designed. So we are not providing pipe sizes and detailed configurations for those. So that part is not factored in this way into the system. And for the head of the pumps, we have general assumptions which we take into account, and we are just calculating with those. So it's not possible to add as a user input that I would like to have this and that. But for the typical reactor volumes and the typical sizes, we are supporting what is available on the market.
Hey, Adam, can I ask another question? Okay.
Of course. Yep.
One of the sort of selection criteria that we're starting to see much more applicable or relevant is greenhouse gas emissions, particularly process emissions, whether it be methane or whether it be nitrous oxide. Is there anything in the tools right now which help us evaluate different configurations and options with respect to those process emissions?
Yeah.
This is a hot topic.
Yeah.
Really hot topic. Letty, go ahead.
Okay, yeah, actually carbon calculations is one of my my favorite topics. So I just personally like this part, and we are working on it. We have lots of questions regarding this because at many countries, carbon footprint and different carbon limitations are just going in and start to be a requirement by government and so on. But actually it's not available there, and I'm very sad about this, but we are working on it, and personally I really like spending time on working with this.
Brilliant, thank you.
As a reminder, the link for your free design to register and try it out for yourself is in the chat. So if you click that link and enter an email address, you'll be able to have access to the tool and run your first design on us. So I highly encourage you to do that, to sort of test it for yourself and let us know how the experience is.
Okay, Adam, if I can share my screen, then I will have one more slide which I can show. Okay, I'm going back to this one. So yeah, as the last question was about evaluating different options, this just reminded me that I have put together this small table. This is really a very mini example of what can be done as a kind of feasibility study by the tool. So what I have put together is I have run different designs for the same design average flow, for the same minimum temperature, for the design MLSS of, okay, sorry, something happened to my computer. So for the same design MLSS, and I have just compared the different outcomes of the tool. So the delta P to remove per influent COD was 0.01, which resulted in an anaerobic mass fraction of 0.16. This is regarding the calculations which I have mentioned at the very beginning of my presentation. So the different configurations I have tried was the UCT without primary, UCT with primary, 3-stage Bardem flow without primary, 5-stage Bardem flow with primary, and the simple 4-stage Bardem flow. So this is something without biological phosphorus removal, but the primary clarifier was there. And just very quickly, I was able to put together the designs, run the documents, run the design, and just receive the documents and put together this table. So what we can see here is, for example, which we all know that what are the effects if we have a primary clarifier. So if we have this designed with primary clarifier, it is going to be smaller compared to the one without primary clarifier. Of course, because we are removing the solids and lots of carbon loading from the biological part. So nothing surprisingly, but it's very easy to compare them and show the differences quite fast from the different options. Also,
Lexi, when you say fast, like give us just an estimate of how much time it took you to run these and put this table together compared to a traditional process.
Okay, so actually this was 5 projects, and as I'm quite familiar already with the tool, it took me about 20 minutes to run all of these projects. And put together the table, I think maximum 20-30 minutes, just to gather the information from the different documents. But yeah.
And as a process engineer without the software previously in a previous life, how long would this typically take a process engineer or another engineer to put this together?
Actually, at least one process design would take about minimum 8 hours. And now this is about the pure process part, and I'm not taking into account the equipment selection and the civil part, only the process. So at least 8-10 hours per design as a minimum, which means that about, for this 5, about 50 hours to have all of these. And actually, maybe that part would not mean that I have all these fancy documents put together, just the numbers, and I would still have to spend some time on putting together the technology description and so on with all the stuff there. So also I have added this part, the Bardenfo, the A2O configuration, again, without and with primary. So what we can, for example, see is that the UCT configuration appeared to be bigger in terms of reactor volume compared to the Bardenfo A2O process. And the reason for this is, again, very obvious, because in the UCT configuration, we have the MLSS in the anaerobic zone lower compared to the rest of the facility, because we are having a separate MLSS recycle line for the anaerobic zone. We cannot have the same exact MLSS available. And as we would like to provide the same anaerobic mass fraction, so the overall anaerobic mass available in the system should be the same in terms of UCT or Bardenfo configurations, it will lead us to a situation that UCT appears to be bigger in terms of reactor volume compared to the Bardenfo selection. And the last one was just a non-BioP version, which is of course smaller in terms of reactor volume. We don't need the anaerobic part, so yeah, it's very normal that it's going to be smaller. But I have already added that we will have the ferric dosing. So that means in terms of operational cost, this can go up. Many facilities don't really like to have chemicals, so they try to operate the plants in a way that as less chemicals are used as possible. And also the ferric dosing increases the total starch production because of the extra chemical sludge. So the overall OPEX could be different for the non-BioP version compared to the BioP version. So but this table is just about the reactor volumes and different retention times. And I just wanted to highlight these different MLSS within the anaerobic zone. And just the reason what I wanted to show this to you is that how easy to put together these kind of comparisons within the tool. Just very shortly, you can enter all of your inputs and just compare the different options. And you don't have to do all the full process design for the different options. And this is the same for different technologies as well. Now, this was purely for CAS, and I was not focusing on adding any other technologies into this stuff. But I think showing this mini comparison can just show you the direction that how other maybe a little bit more complex comparisons could be put together.
Letty, we have a question from Mikhail, which is one we often get. And so I want to be sure to address it. And that is, how can I see the causal graph? Basically, how to understand what other implicit data was used to build the model and accepted for calculation. In other words, right, what's the calculation happening behind the scenes and how can we look at what those are?
We have at the background, of course, available a very detailed technical calculation document showing all of the, so everything, how we decide, how we select the different equipments, how we select the units, what are the design considerations, and that can be provided for the users. So this can, I really hope that solve these questions, that what's happening there.
One of the documents, as well as the technical description document and design basis document, which can also help in some cases. And then another thing that we do, Mikhail, and for everyone else on the call, is that what Letty presented today and what you can run a design in for free is a design tool that's based off of publicly available engineering calculations or textbook design rules. So sometimes we'll refer to this as the Metcalfe-Eddy design generator, effectively, because all of the design rules are based off of textbook values, white papers, etc. What we will often do, though, for specific clients is they have their own ways of selecting and sizing equipment or creating renderings and having safety factors on buildings on the civil side and a host of other rules. So what we'll do with them is actually walk through all of those design decisions and calculations they use and configure the tool so that when the outputs are generated, they look just like your outputs, not like Metcalfe-Eddy or public design outputs. I wanted to make a clear distinction between the two. So we do work creating unique versions of the software for specific clients. It's not just the publicly available tool that everyone's using.
And just one thing to add, that's the reason why we are trying to add more and more input fields to the user interface. Just a very simple example regarding the clarifiers. Previously, the loading rates for the clarifiers were not user input fields. We were just using the numbers coming from the clarifier design textbook. But this was just coming up that user would like to have more control about this and want to know the exact design numbers. And however, at the end, in the technical description, it is there that what was the design loading rate which we have applied. We have allowed and opened this up on the user interface. So now users can define themselves, for example, for the loading rates. And this is just constantly growing on. I mean, we are adding more and more input fields, so you will have more and more confidence, hopefully, in the tool.
Right, I know we're getting to the top of the hour, so we will be closing the webinar shortly. Ridian says, need to leave, but very impressive. We'll definitely try the free design to compare against one of our previous projects. Excellent. That's what we hope you do. We hope you log in, use the software, give it a shot. Obviously, your design logic is going to look different than ours. So I wouldn't imagine it's going to be a like-for-like comparison. Chances are every project has its own nuances. Every engineer has their own way of designing. But that's what we will work with you. If it's something that looks, interesting to you, we're happy to talk you through how we would configure the software to make it work for your specific design practices. So thank you everyone for joining. We'll keep the webinar open a couple more minutes. Again, we hope you use the software. The link to register was in the chat. We'll be sending it out afterwards. And do not hesitate to reach out if we can help you with anything.